All right, folks, welcome back to our discussion of two-sample t-tests. We're going to be talking about the second form of two-sample t-test. Hopefully it's not blocked by my shoulder. It looks like it's not. Again, when we have two samples and a within participants design where the same people are measured multiple times, once for each condition, so they experience both conditions and the DV is measured after each one, we would have a related sample situation. This sometimes gets called the dependent samples t-test in other textbooks because it's of its similarity to the independent samples test. But the idea there is the samples are independent if there are different people in them. They are dependent or related if we have the same people in them. So the scores that the situations we're going to be interested in here, situations where we measure each person twice and the scores are dependent. We might measure people's test scores before and after studying something. We give them a similar test twice. We might measure people's weight before and after using a diet. Again, really common type of everyday study. We measure the change in the same group of people. We might measure people's reading ability under bright versus dim conditions, something we could measure with the between participants design, but we just rather would do it this way. That design overall is called a repeated measures design. The ones that we have talked about, like the examples up there, are within participants designs. There also are rarely what are called paired samples designs. Paired samples designs are interesting because there are actually different people in the different conditions, but you are matching them on some kind of a key characteristic. So you find people who are identical on some kind of a key pre-existing difference, and then you randomly assign it so that one of those winds up in each condition. Basically, it allows you to control which members of different pairs wind up in those different conditions. Here's the thing about paired samples tests. They exist in the real world. They're pretty rare. We're not going to talk about them anymore. I'm not going to throw any curveballs like that in your test questions. So if you see a two-sample test, all you have to worry about is it between participants? Okay, it's independent samples. Is it within participants? Okay, it's related samples. I'm not going to throw any paired samples designs in there. So again, the t-test that we use here is the t-test for related samples. We'll talk about some of the basics of that, but first a little bit of a segue to talk a bit more about why people might use a repeated measures or within participant design. We're going to talk more about this in some future modules, but for now, one of the biggest differences about within participants designs is they eliminate a major source of error, what you might call noise. Remember that we're always very concerned about things other than the independent variable that could affect the dependent variable. We want to isolate the impact of that IV as much as possible. One of the things that can happen for pretty much any variable you could measure, people are already going to differ on it before the study starts, before they experience the independent variable. If your DV is irritability, some people are already naturally more or less irritable or more or less irritated right now before the study even starts. We try to cancel out those individual differences with random assignment, but random assignment is not perfect. Some of the difference between our conditions could be due to just the more irritable people mostly winding up in one condition and the less irritable people in the other. That is not a concern in a within participants design. Why not? People are the same. It's the same people in both conditions. So we know that there's no difference between the average person in the control condition and the average person in the experimental condition because they're the same people. So this results in eliminating a major source of error or inaccuracy. It tends to lead to a smaller denominator for our t formula. And remember, the smaller your denominator gets, the bigger your result's going to get. Basically, by eliminating this, we get more clarity and we are more likely to find a significant relationship and a stronger relationship in a within participants design. That's why they're referred to as more powerful. Most repeated measures designs are going to need fewer participants because you're getting multiple measurements from the same people. You don't have to measure as many people, so it's more efficient that way too. This is especially effective if the population you're looking at is pretty rare. People with a specific disorder, for example, that's pretty uncommon, or people from a specific set of environmental conditions that aren't that commonplace. Repeated measures design lets us get kind of more bang for the buck. They're also used a lot, like in that dieting example, to measure changes over time. Either natural changes, like a developmental psychologist might look at, or an intervention like our reading comprehension training example or our weight loss example. And again, it increases power overall. So here's our major change. Here is the biggest sort of shift that we've had in the hypothesis test yet. Because we are measuring the same people twice, we are going to be taking the two scores that we get from each participant and calculating what's called a difference score. A difference score is simply the difference between the scores the score that a participant had at one measurement and the other. If you are measuring them consecutively, like change over time, you put the second measurement first and subtract the first measurement from that. That can seem unintuitive, but again, think about it this way. If your reading comprehension improved after some kind of intervention, you would want to have a positive difference score to reflect that. And subtracting the early measurement from the late measurement is the way that you would get that. So each participant gets a difference score. That's just the difference between their two measurements. So everybody winds up getting their two scores boiled down to one that reflects the difference between those scores. Everything then revolves around those difference scores. It looks very similar to a single sample t-test, actually, where the single sample that we've got is now those difference scores, and our basis of comparison is the null hypothesis that those difference scores will be 0 on average. So the null here is just that the average difference score is 0, that the two circumstances under which we tested our people are essentially identical. So we start with the idea that the average difference score in the population is 0, and we see if our sample data allows us to reject that. That results in, again, everything revolving around those difference scores. We calculate variance for them in standard error. We calculate the mean difference score. It's all very easy to calculate. You just have to remember why you're doing it and what you're doing. That has to be calculated. Notice for the first time we see different symbols in our null hypothesis. Here, our null hypothesis is that mu d equals 0. What does d mean? I hope you can already guess. It means the average difference score in the population. The average difference score in the population is 0. Our research or alternative hypothesis is that the average difference score is not 0. The mean difference score of the population is somewhere different from 0. Because it's two-tailed, we don't specify in what direction. And here's our test statistic. Again, it can look a little intimidating. Let's look at it. The average difference score in our samples, okay, that's just the same as subtracting M1 or M2 from M1 like we did in the independent samples formula. It's just the average represented as an average difference score, minus the average population difference score, which, much like the independent samples formula, we treat this as 0, so it might as well not even be there. Why is it there? Sometimes you'd have a null that the average difference score is something other than 0. We're never going to do that in this class, though. So we basically eliminate that. You end up with the average difference score in the sample divided by, you can probably guess, this is the standard error of those difference scores. So same thing. We've got a deviation score on top. We give it context by dividing it by a standard error. The only difference is it's all revolving around those one set of scores called difference scores. So this is our second point of emphasis of this module. Again, because we are measuring every participant once in every condition. We have the same people in each group. By the way, quick thinker question. What would you do in this design if somebody gave you a measurement in one condition and then walked out or refused to answer in the second condition? Now we don't have the same number of scores in each condition. The answer is you drop their data. You would eliminate their scores. You wouldn't use them. You need to get measurements from every participant in every condition to use that data. Anyway, because we're measuring the same people repeatedly, we boil their scores down to these difference scores. Score 2 minus score number 1. Sometimes it's important which one goes where, like when you're measuring the passage of time. Sometimes it's arbitrary. We'll see how we account for that when we get to our example problem. But once you've got it, it looks a lot like a single sample t-test, or an independent samples t-test really, but a little bit closer to the single sample because we now have just that one set of scores, those difference scores. Here's a really key point. Our N and our degrees of freedom, we've seen them a lot in the past. Those are tied to the number of participants, the number of people you measured, not the number of scores. This has actually always been true, but in every other research setting, every other hypothesis test, we only measured everybody once, so the number of participants was exactly the same as the number of scores. So again, it's a very common mistake to count up the number of scores and treat that as the N. Do not count the number of people who were measured, or you will screw up multiple parts of this process. So if you measured 10 people twice, your N is not 20, the number of scores, it is 10, the number of participants. So again, we are going to take those difference scores, calculate a variance. We're going to change that into a standard error just as we normally would. Again, the first thing to do is calculate those difference scores, which we'll practice doing in a bit on the next video. Then a sum of squares, just like you normally would. The only difference is that what you're plugging in there are those difference scores. Then you change that sum of squares into a standard deviation by dividing it by the degrees of freedom and taking the square root. And degrees of freedom is based on the number of people you measured, not the number of scores. Then we turn it into an estimated standard error using the same old formula. The only thing that's really changed is that capital letter D showing up everywhere. Take your standard deviation, divide it by the square root of n, and again, notice how important it is to get n right. It's the number of participants. That gives us our estimated standard error. That's the end in terms of setup. All that's left is to cover a short example, which we'll do in the next video. See you there.